Hello everyone! Today we continue the study of the ferromagnetic order parameter. We shall learn its temperature dependence in the Ising model. Also, we shall introduce the ground and excited states of a ferromagnet and shall see that the energy spectrum has the gap. We shall see that the first excited level of energy is separated from the ground level by 2 theta, where theta is the Curie temperature. The Curie-Weiss equation for order parameter at zero magnetic field takes the following form, where theta is the Curie temperature. Since mu Iz lies in the range between minus mu b and plus mu b, therefore the order parameter lies in the range between minus 1 and plus 1. Recall that x is equal to 0 if t is greater than theta, and x is not equal to 0 if t is less than theta. Magnetization is described using the following expression, where m0 is the maximum possible value of magnetization. In other words, all magnetic moments have the same direction. It is clear that magnetization is equal to 0 if t is greater than theta. Let us analyze the temperature dependence of magnetization at temperatures below the Curie temperature. At t is much less than theta, or in the case when t tends to 0, we can expand the hyperbolic tangent in a series for large values of its argument. We assume x is greater than 0 for clarity. Therefore, for the order parameter, we obtain the following expression. Let us try to solve this equation iteratively. From the Curie-Weiss equation, one can see that if there is a solution at x is greater than 0, then there is a solution at x is less than 0. Therefore, we can write the following equation. Thus, the magnetization takes the following form. One can see that if t tends to 0, then m tends to m0. In the case of t is less than theta and t tends to theta on left, we can expand the hyperbolic tangent in a series for small values of its argument. Therefore, for the order parameter, we obtain the following equation, and magnetization can be described in the following way. Resulting characteristic temperature dependencies for order parameter and magnetization are shown on the figures. Let us analyze the results obtained. The order parameter and magnetization are identically equal to 0 at temperature is greater than or equal to theta. At temperatures are less than theta, both x and m increase monotonically with temperature decreasing to values 1 and m0 respectively. In other words, in the system of magnetic moments, the order occurs under cooling below the Curie temperature, and this order increases as cooling increases. In other words, the temperature decreasing leads to orientating the magnetic moments along one direction. So, order parameter and magnetization are the quantitative measures of ordering. Recall the Hamiltonian in the Ising model in the absence of magnetic field. At zero temperature, the energy of the system is minimal, E is equal to E0, where E0 is the energy of the ground state. If Psi0 is the ground state, then the following expression is right. It is common knowledge that any state of system of magnetic moments is defined by a set of numbers sigma 1z, sigma 2z, and so on until sigma nz, which are equal to plus 1 or minus 1. The total amount of these numbers, sigma nz, is equal to capital N. What should be these numbers for the ground state? Recall the following equalities. Therefore, we have the following equation. Thus, we can rewrite the Schrödinger equation in the following form. So, energy of the state with arbitrary set of sigma nz is described in the following way. Since both sigma Iz and sigma Jz are equal to +1 or -1, then the product of sigma Iz and sigma Jz is equal to +1 or -1 for any pair of magnetic moments as well. Thus, the energy will be minimal if sigma Iz is equal to +1 and sigma Jz is equal to +1, or if sigma Iz is equal to -1 and sigma Jz is equal to -1 as well for any Ij pair. As this takes place, the energy of the ground state is described as follows. In the language of ferros, the equality of sigma Iz to +1 is equivalent to arrow up, and the equality of sigma Iz to -1 is equivalent to arrow down. Hence the ground state of the system is doubly degenerated. In other words, all magnetic moments have the same direction and aligned along or against the selected axis. Thus the ground state can be presented as all ones or all minus ones. The energy of the ground state has the following form. Now consider the first excited state Psi1. Let us find its energy E1. For the sake of definiteness, we shall choose one of the ground states. The slightest excitement can be written in the following way. Therefore, for the energy E1, we can write the following manipulations. Finally, for the energy of the first excited state, we find the following expression. Thus, the energy spectrum has the gap. In other words, the first excited level of energy is separated from the ground level by 2 theta. In this lesson we obtained the temperature dependencies of the ferromagnet or the parameter and its magnetization. We showed that the temperatures are less than Curie temperature, both order parameter and magnetization increase monotonically, with temperature decreasing. In other words, in the system of magnetic moments, the order occurs under cooling, below the Curie temperature, and this order increases as cooling increases. This is the classical example of second-order phase transition. Recall our very first lecture. This situation is very similar to the so-called evenly painting the sheet of paper. The order parameter and magnetization are the quantitative measures of ordering. In the second part of this lesson, we introduced the ground and excited states of a ferromagnet. We found that the ground state, in the absence of magnetic field, is doubly degenerated. Note that the magnetic field takes off that degeneracy. Try to prove this by yourself. We also introduced the slightest excitement in ferromagnet, which is characterized by the overturn of only one magnetic moment. Finally, we found that the first excited level of energy is separated from the ground level by 2 theta. So, the energy spectrum of ferromagnet has the gap.